go from the current slide.
I've almost got my chapter 5 test done.
Uh-huh.
But I hung up on one here. I'm trying to, I hope I can find one.
Okay.
Similar.
All righty. I'll put a marker in place here. Chapter 5.
Section 5.5.
5.5. That was a long chapter. Okay.
I'm pretty strong about the other questions. I'm just stumped on this one for some reason. I can't remember. Can't really find one similar to it.
Okay, let me see if I can help find one. This is test 2, is it? Okay. And which one?
Number 8.
Number 8. F prime, if alpha of t is equal to t to the 8th nine okay. It looks like the group 39 to 60 would be closest to it, but I don't know if any of those quite fit your bill or not. 43, 44 are somewhat similar. Or are they? I mean, are they close enough? See if there are any at the end of the chapter. On the review exercises on page 401 is 47 through 52 would be somewhat similar. No, but not exactly. Oh. Then there's ones like 75 to 78 that would be a little bit similar. So page 358, looks like 39 to 46 would be the closest.
I think 43 was
On which?
on 358.
Yeah, okay. All right, we'll do it on the arc length page. Okay, so this is page 358, is that right? Let me get my pen set up. Page 358, is that the one we decided on? 5.5 exercises. Number, which one? 43. Alright. It's finding a derivative. Find the derivative of this function, and the function is alpha of x is equal to x times 9 to the x. Alright. So we're looking for f prime of x. Now, first, foremost, what rule are you going to have to use?
The chain.
Second?
Well, Yeah, the chain rule, right? 'Cause
Ultimately, yes, but first you got to use
the power rule.
not power. You may have to use that, but not really. It's the product rule. That's a product of two functions, right?
Oh, yes.
Okay, so start with the product rule. Okay, and how does that go?
The derivative of the first,
Which is
the 1.
1 times
1 times 9x.
9 to the x plus,
All right. And then the 9x.
okay, 9 to the x, that's the derivative of the first times the second.
Yes, sir.
Okay, plus,
And then 9x is the derivative of the second one, isn't it?
okay, yeah, that is the second, yeah. Okay, so we're doing derivative of this, which is 1 times this,
Right.
that's that part,
Right.
plus,
The derivative of the second times
yeah, derivative of the second times the first, okay. So I was going to put the x.
the. Oh,
Now, what is the derivative of 9 to the x? Okay, and this, just to make sure you get it right, go back to, on page 354, derivative of any a to the x is
log of a times a to the x.
yes, and in this case that would be
It would be log 9
log 9,
times 9x.
9 to the x. Okay,
So that jot it down.
all right. Now, I can't think of much else to do to this except maybe factor out a 9 to the x. You don't have to, but it might make it a little simpler. And then you have 1 plus x log 9. And normally I'd say log 9 times x, but then you might think that's log 9x, and it's not x times log 9. That, either one of those is perfectly fine to give as your answer, right?
Yes. Okay. I'll feel better about this.
Okay, good deal. And here's DeMarcus. Okay. All right, any others before we move on? Does that make sense? We were doing from the second test a similar problem in the book on section 5.5, exercise number 43. Okay. And you don't have to do that next step. I just wrote it down. I thought maybe the answers would be here, but I don't see them.
Did you get a previous one too?
What's that?
Was that the only one you did? Or?
That's just, he asked about it, so we did it. Did you have any others you wanted done?
Got here late.
Okay, I think it was hard.
I said there was one, but I got here late. I didn't want to burn you with it.
That's what we're doing, so you got one, we'll do it.
Number 9.
What's that?
Number 9.
Number 9 on that same page?
Yes.
Okay, number 9.
Oh, opposite.
Okay. Evaluating a logic expression, is that the one you're
I'm
talking
talking
about?
about number 9.
Oh, on the test. Oh, okay. Well, I don't do test questions, but I will do one like it in the book. So test 2, number 9. That was one of the latter sections called inverse trigonometric functions. And it wasn't even taking a derivative of it. It's just basically something like on page 379, 29 to 36. Or even more so, 25 to 28. Maybe 26B might be very close.
If you factor out two things,
What's that?
if you factor out two things, it's still 1 plus
If you factor out what?
2
Out of where?
out of anything. Like if you're just going to factor out, like say you had another x in there and you factor out another x, would it still be 1 plus?
Yeah, okay. Say if you had an X here.
Just anywhere in there, you could factor out the 9x and the.
Yeah, if you had an X here and there, yeah, you could do that. You don't have to factor it. I'm just writing it a little simpler.
Well,
that answer up there is perfectly fine.
Would it still be 1 plus though if you have 2 up front now? No. So
Okay. Yeah, if you had an X log X, X9 to the X here, and you had an X9 to the X there, factor that, it would still be a 1.
Still be a 1 here.
Yeah, if that's all you had. Now, if you had a XY, not that you would, XY log, 9 to the X, and you only had an X over there, then it would be a Y left here.
Right.
Or a 7 or whatever else. If you had
Yes.
Okay. I'm sorry, I can't hear.
I was saying, I think that might have been the wrong one I had a question about. I had a question wrong about it, but I was found something else, so sorry. Because like you said, you recently done it, and that's relatively simple. Goes on all the time.
Okay. Are we talking about the one on page 379, 26B? Is that what one that you're thinking of? Or I don't know what you're asking about. You said number 9 on the test, right? Or not?
I previously did, but that was the wrong one. I had
Oh.
a question mark probably by mistake. It was number 7.
Oh, number 7. Oh, okay. Sorry, I misunderstood. Okay, find the indefinite integral that. Okay. All right. Okay, that's probably going to be goodness. It's a pretty straightforward problem, but I'm not seeing. Okay, it's 5.4, I think.
Number 7 was 5.4.
Number what? 70?
No, so number 7 was 5.4.
7 is 5.4, right? Okay. Oh, okay. You're just saying that was the section it came from. Okay. And what we're doing is
So we did something similar to this in class on all of them. Notice the exponent of the exponent, and then there on and find an example of it in the book.
okay. I couldn't understand all that. Say it one more time.
I wonder if we did something similar to number 7 previously in class. I just didn't remember.
Number what?
Number 7 on the test. I know we did something previously similar to it in class. I just forgot some of the steps. I was trying to find an example of the problem in the book.
Right. That's what I'm. You found one?
I'm looking for it.
Oh,
Make sure I-
yeah. That's what I'm doing too. Is something like number 112 on page 350? I don't know if that's the same, but it's
Similar.
somewhat similar.
Only difference is with fractions and the exponent, but there's two.
Would that be okay?
Should be.
Okay. And the other thing, it says an indefinite integral. This is a definite integral, but I mean, not that big a difference. We could do it as an indefinite integral if you want to, right? Or we can do it as definite. I don't care. You want to do the 112? Okay. So this is page 350. This is 5.4 exercise. And that's number, 112. Goodness gracious, talk about a bunch of problems. Okay. You want to do it as is or indefinite? Indefinite. Okay, we'll leave off the limits then. X squared e to the x cubed over 2. I know it's, I moved the thing and it wiggles it. I don't know. Over 2 dx. Yeah. Okay, I'm just making a big deal about it. Okay. Now, how would you approach a problem like that? Oh, okay. As in maybe a substitution? Yeah, okay. Daniel's here. Okay. So let U be something. And what would you want the U to be here? The what? You may have said it right. I can't hear.
I said the x squared of e, but I realized that's a mistake because it wouldn't be x squared e. It'd be like maybe the exponent like the x cubed over 2.
Yeah, that sounds like a good idea to me. X cubed over 2. Okay. Then, that's the next step. We're on page, we're doing one similar to a test question 7 on the second test, and we picked one out of section 5.4 on page 350, number 112. And we changed it a little bit, but not much. Okay? Then what's the next step? du is equal to 3x squared over 2. Perfect. dx. Don't forget that part. Okay. Now, how does what we have down here look like what we have up there? Up here, this part is just x squared dx. So if we had just this part, that would be exactly what we have up there, right? So what do we need to do?
Multiply by 6, but technically 3 over 2.
By what?
3 over 2.
No, 2 over 3.
2 over 3.
Yeah. Because if you multiply 2 over 3, this goes out and that goes out, right? Right? Multiply by the reciprocal. All right, so now this then, 2/3 du is equal to x squared dx. Okay, I think we're ready to roll now. So what is our new integral? Okay, that 2/3 is on the outside. We don't really need it inside. And that leaves us a du. And you have the du would then be the x squared dx. So that would cover that. So there's your du. And then your rest of it is e to the
x cubed over 2.
No. What do you call that? U. E to the U. That's why we chose it, right? Okay. I think we can do that one, can't we? 2/3 antiderivative of e to the u. That's why it's my favorite of all time. It's e to the u, exactly, plus c. Okay? But now we go back and plug in what u is, or u are, or whatever, okay? 2/3 e to the x cubed over 2 plus c. That it? Right. Make sense? Yeah or nay? Yeah. Okay. Any others? All right. All right. Well, if no more of those, then let me put my pile back in order. Otherwise, I'll lose it forever. Okay. All right. And let's go back to beginning, where we are today, and that is arc length. Yes, and this is the slide we were on. Like you said, we just started talking about arc length. Now, and if you got your books, this is page 474, chapter 7, applications of integration, and 7.4 is arc length and surfaces of revolution. Okay. What revolt? No, not like that. Okay. Definite integrals are used to find arc lengths of curves, and then once you have the arc length of a curve, you can revolve that around an axis of some nature, and then you can get a surface. Okay, not doing volumes now, but that would be a surface. In either case, an arc, or that's also a segment of a curve, that's what we mean by an arc, is approximated by straight line segments whose lengths are given by the familiar distance formula. Distance is equal to change of x squared plus change of y squared, square root of x, right? If you have 2 points here and here, and you want to do the distance here, you do this distance squared plus that distance squared, gives you that distance squared, and take the square root of that, and that gives you that, right? Okay, good old Pythagorean theorem. Now, a rectifiable curve, whatever that is one that has a finite arc length. Okay? In other words, a curve that goes to infinity probably isn't, you can't say always, probably isn't going to have a finite arc length because it keeps going. Okay? But one that has a finite arc length, that's called rectifiable. Okay? So you need to rectify it by all means. Okay? You'll see that a sufficient condition for a graph of a function f to be rectifiable between a f of a, that's a and whatever its value is, and b f of b, whatever its value is, then that is that f prime be continuous on that interval from a to b. Okay, that's all that's necessary for f prime to be continuous. And if it's going to infinity, it's probably not going to be continuous, okay? Because how can you take a derivative somewhere at infinity? Okay. Such a function is continuously differentiable on AB, meaning you can just keep taking derivatives on that. And its graph on AB is a smooth curve, okay? Can't have any cusp in it. That would be differentiable, okay? The first derivative would not be continuous if you had a cusp, if you had a corner, or if you had a gap, okay? Couldn't be, okay? So f prime must be continuous. So it must be continuously differentiable, and the curve has to be smooth. Okay. Now, yes?
I was just going to ask you real quick, why are points not differentiable? Because you'd think if you get small enough, it'd be like, a positive on this side and then
Okay. Let's say we had something that goes like that. Okay, if you're taking the derivative here, That's a positive derivative, isn't it? But right here, it becomes a negative. Not continuous. It can't go from being pretty positive to pretty negative and be continuous there, right? The derivative has to be continuous. The function's continuous, yeah, but if you go smaller and smaller and smaller, it still looks like that, and like that, and like that, It's still the derivative. The function's continuous, the derivative is not, because it's positive on this side, negative on that side. Ne'er the twain to meet.
And so like it's never zero in there.
Never zero, yeah. Whereas something that went like this, yeah, that's smooth. That's positive, 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 but less and less positive, less and less positive, goes to zero, and then negative, 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 you get more and more negative. Yeah, that one's rectifiable, that one's not. Yeah. Good deal, good question. Okay, so let's consider a function, y is equal to f of x, that is continuously differentiable on some interval from a to b, okay? You can approximate the graph of f by n line segments, okay, whose endpoints are determined by whatever partition you choose between A and B, okay? So A is going to be your x of 0, and it's going to be less than x1, less than x2, less than x3. Finally, you get to x of n, or whatever that is, however big n gets to be, that will be your B point, okay? So here are that is the arc length between there. That's not a particularly easy thing to measure, okay? But if you did the diagonal line between these 2 points, that's going to be almost the same length, very close. Here it's a little less, but still pretty close. And then here you have another one, and there you have another one. Okay, so that would be a little less, because the shortest distance between 2 points is a straight line. That's what you're doing. The curve is not the shortest, but it's just a little bit long, okay? Now, to get it more accurate, put more points in here, okay? Do it from here to here, and that's even closer, and here to here is even closer, here to there is even closer. So just get your interval smaller and smaller and smaller. Ultimately, your delta x becomes a dx. You have an infinite number of them, and that's going to track out your arc length pretty well. In fact, when the limit is the delta x goes to 0, then you're going to track exactly your arc length. Okay? So, what we call the length of the curve between these any 2 points is usually s. Arc length is usually referred to as s. Okay. And what you're going to do is do an integral of these lengths that was on the previous slide times dx. Okay? So, your delta x here is your change of x. Your delta y is the change of y. And this thing right here is the square root of delta y, x squared plus delta y squared, right? That's what this would be then, okay? And let's see what they do on the next slide, okay? By letting the delta x be the difference in x between the 2 intervals, delta y being the difference of y's in the 2 intervals, you can approximate the length of the arc. Okay, it's a summation. The arc length would be approximately the summation from I is equal 1 to n, however many increments you have there, square root of x of I minus x of I minus 1. That's your delta x squared plus your delta y squared. Okay, that's going to be your approximation of the arc length. Well, okay, I just named them that. They said they were. Now here comes the tricky part. It's not that tricky, but it is a little bit. Let's divide everything inside by delta x squared, delta x of I squared. Okay? There's Catherine. And Jordan. Nope. And Vince. Yeah, I figured. Vince is here. And Jordan gets here. We'll have perfect attendance again today. Way to go. This is opposed to my next class, Cal 3, which I have had several classes, have had zero people here, and I've been talking to myself the whole time. So I really appreciate your attendance, okay? Now, what we're going to do is divide, well, here's what we're going to do. Almost. Multiply this one by delta x sub I squared over delta x sub I squared. It looks like a dumb thing to do, but there it is. And then we'll factor out the delta x of I squared over here. But that's under the square root. When you take the square root of the square, you just get delta x of I. Well, what do you have here? The integral, the radical of 1 plus dy dx, which is your derivative of your original function, okay? In parentheses squared times your dx. Change this to an integral. That could, from the delta x to the dx, and this becomes the square root of 1 plus derivative squared times dx. There you have it. Now that approximation, as your delta x goes to 0, as your del goes to 0, meaning your interval gets smaller and smaller and smaller, which is the delta x going to 0, then this goes to dx, this goes to dy dx, this goes to the integral from a to b, and there you have it. As the n goes to infinity, these things are happening. So there is our, well, going backward, the limit of this thing is the del, that partition, the longest length of the partition is going to 0. The limit of that is going to become your interval. I'm sorry, it's just going to show up on the same page. Okay? But because f prime exists for every value on that interval, the mean value theorem guarantees the existence of some value in there, then that's going to be some f prime. And I don't know, I mean, it seems like to me if you just did the interval here, the dy dx squared times dx, that would give it to you. Why do you need to bring this thing if there has to be a c sub I in there? It's true, I mean, absolutely, the mean value theorem guarantees that, but so what? I mean, why do that? This is what you're going to wind up with. Whether or not you had the CI in there or not, you still wind up with exactly this. The integral from a to b, square root of 1 plus f prime squared dx. Whatever your function is that's your arc length, take the derivative of it, square it, add 1 to it, take the square root, and integrate that. Okay. So it's a sort of a long, kind of weird process, but it comes directly from your distance formula, your Pythagorean theorem. So S is called the arc length between A and B. It's that integral from A to B. Now, if some of you are saying or thinking, wait a minute, how can I come up with a function, f, any old function f, that when I take its derivative, square it, add 1 to it, then take a square root of that, I get something that's integrable. It's a pretty tall order, okay? Yeah, there's different techniques for doing things like that, but it still comes out being, there aren't very many functions that this is easy to do, okay? A lot of times you wind up doing them numerically, just because that's a tall order to fill. You have a function f, and when you take its derivative, square it, add 1 to it, then take the square root of that, you get something that's easily derivable. Integrable. Yeah, fat chance of that. And there are some, and we will do some, okay? But you just can't take any old function and guarantee that's going to work. Theoretically, it does, but practically, it may be very, very difficult to do, okay? So, this leads to the definition of arc length. Let y be some function of x represent a smooth curve on an interval from A to B. Notice we can't have any places where the first derivative is discontinuous. Okay? That means it has to be smooth. the arc length of F between A and B then would be, just like we said, the integral from A to B of the square root of 1 plus the derivative of that function squared. That's all into the radical dx. Okay? Now, what if you had going the other way? X is a function of y. Okay? X is equal to g of y. Then the arc length of that between C and D, this is on the y scale, the arc length will be the integral from C to D of the square root of 1 plus g prime of y squared times dy. So here you're doing the increments of y, here you're doing the x. Okay? Whichever is easier to integrate. And sometimes neither one of them are easy to integrate. So here's example 1. Find the arc length. Oh, this one's going to be pretty easy. Find the arc length from x1, y1 to x2, y2 on the graph of f of x is equal to mx plus b. What does that represent?
They usually know on the last test.
Is what?
They usually know on the last test or something. That's when they let the point slope from with the
That's slope-intercept.
slope, yeah, slope intercept.
Yeah, that's a straight line, right? And the arc of a straight line, it's just going to be the length of that line, right? No arc involved here, no curve in it. It's just going to be the length of the line, okay? And we know what the length of that line is, right? But let's go through the motions. What's the first thing you do?
Add 1 to it.
Okay, not yet. You take a derivative of it, okay? So f prime of x is equal to what? Anybody? M, exactly. The slope. That's the first root of the straight line is the slope. And then what do we do to it?
Add 1.
Not yet. Square it. Okay, you square it. So f prime of x squared would then be m squared, right? Okay. Now, you do what?
Add 1.
Add 1 to it. All right. So then you do 1 plus f prime of x squared, and you get 1 plus m squared. And then what do you do with it? Take a square root of it. Okay. That's the plus there. Okay. Okay. And then that's what you integrate. So you integrate from x1 to x2 of the square root of 1 plus m squared dx. This is a hard way to do it, okay, but it's doable, okay? And, of course, 1 plus m squared is a constant, right? Square root of 1 plus m squared is a constant. So you could pull that on the outside, and you just have the integral square root of 1 plus m squared, because that's a constant, integral from x1 to x2 dx, and that would be square root of 1 plus m squared. It's so ridiculous doing it this way. Be x 2 minus x1. Okay. Now, what is your m? That's y2 minus y1 over x2 minus x1, right? Yeah, okay. So m squared would be this thing squared, would be y2 squared minus 2y1 y2 plus y1 squared over x2 squared minus 2x1 y1 x1 x2 plus, get out of there, okay, plus x1 squared. Not, I don't know if I needed to do all that. No, I didn't. Back off. I don't think I did. Yuck. Sorry. Extra writing. I hope you weren't following me too closely. That's y2 minus y1 squared over x2 minus x1 squared. Okay. All right. And then add 1 to that, and you get that then would be equal to x2 minus x1 squared plus y2 minus y1 squared okay, one more time, second. Well, because I have it here. I found out what m was, I squared it, and I added 1 to it so I can get rid of this thing. Okay. So I added 1 to it, I added this over this to it. So this over this is 1 plus this. That does give me the same thing there. I'm going to multiply, I'm going to take the square root of this then. Okay. That's the next step. Taking the square root of that. This is the long way to do this. Will be the square root of this. And of course that's the square root of this is just going to be, pull that out of here, x2 minus x1. And that's exactly what cancels that out. And so you wind up with the square root of x2 minus x1 squared plus y2 minus y1 squared. Okay? Which is exactly what you get if you do the Pythagorean theorem between those two things. That's exactly what you get. This is a long way to get to that. So that's what it is. The arc length is that length between here and here. It's a straight line. You just calculate the length, which is square root of x2 minus x1 squared plus y2 minus y1 squared. And I don't know why they had you do that, but they did. They did it the other way. They went and found the m first and then did it. You wind up with the same answer either way you do it. There's at least 3 different ways to do it. Now, I can't remember, did I mention before Christian Huygens? Did I mention him? He's on page 475. A Dutch mathematician invented the pendulum clock. Interesting, I didn't realize that. And James Gregory, a Scottish mathematician, both made early contributions to the problem, of finding the length of a rectifiable curve. So there you have 2 possible paper topics there, Christian Huygens or James Gregory. For some reason, Christian Huygens has been the more notable one of the 2. I don't know why. He was a little bit older, but he lived a lot longer. That may be the issue. Gregory looks like he only lived about 37 years, whereas Huygens apparently lived 66 years. So maybe that's why he's more well known. Gregory died younger, I don't know. So anyway, however you go about finding the arc length, it's that distance between the 2 points. That's all, because that is the arc length of a straight line. Okay. Got there the same way. And that was such an easy problem to have to go through all that to get to it. A lot better. Well, wait. Let me show you how they did it then. And it's a lot of the same steps, only they went through a different approach. Okay. We started out that f prime was m, and ultimately we said m is y2 minus y1 over x2 minus y1. So we did it at different times, but we got that same value. Okay. And then we wanted to show what this integral was, the integral from this to this on square root of this. But your f prime being this, where I put it as 1 plus m squared, and then figured out what m squared was, they're going to start with this right here, f prime, square it, and away we go. You see, the f prime is that, so you're going to square it and do a 1 plus that under the radical. Okay? So, this is your m. There's your m squared. 1 plus m squared is 1 plus this thing squared. Okay? When you square that, and all this is a constant, by the way. These are various points. They're not variables. They're points. So you're just doing this constant out here, which is what I did. That's where this method is leaves a little be desired, times the integral of dx, and that's just x2 minus x1, which they haven't done yet. But what they did here, they're combining a couple steps. We're multiplying, or rewriting the 1 is this over itself. So this, which is x2 minus x1 squared over x2 minus x1 squared, that's your 1, plus this part is that part squared. Okay? And when you do this now is a perfect square in the denominator. So let's see if they take it out now. Yeah, no, they don't yet. They do. Okay. So they evaluate this from x2 minus x1. So that's just this constant times that. Now note that this is in the denominator. You can pull it out of the denominator, just make it x2 minus x1. Pull it out of the square root, make it x2 minus x1. Then those cancel out, and you wind up with exactly that. And again, what's the point of tracking us through all that? We could have just written this down from the very beginning. But it does show that it's consistent. What you know is the answer is what you get as the answer. Okay. Which I guess makes you feel warm and fuzzy inside, right? Huh? Yes, I knew it would. All right. Let's see if they're going to do example 2. Okay. Which is the formula for this is between 2 points, which I said you could have done that at the very beginning and just written it down, and you would have had it. The formula for the arc length is the graph of that same as the standard distance formula, because this arc is a straight line, and that's exactly the length of that. Okay. Enough of that. Let's see if we go to example 2. No! Okay, they did that one which is sort of close to ridiculous, and then the ones that really matter, they skip, and let you figure out on your own. So, let's do example 2. Sorry. Find the arc length of the graph. And if these look like weird graphs, there is a reason they're weird graphs, because you've got to find something that will fit all those things and still be something you can integrate. Y is equal to x cubed over 6 plus 1 over 2x. Oh, one of my favorite functions of all time. Isn't that just wonderful? On the interval from 1/2 to 2. little bit of a timeout first. Okay? Does anyone have an idea of why they wouldn't, if they're doing 1/2 to 2, why don't they just do 0 to 2? Wouldn't that be a lot easier rather than introducing fractions in there? Oh, that x is in the denominator. That's not defined for 0, okay, at all. Not differentiable at 0, at all. So no, we couldn't include 0 to 2. 1 to 2 would have been okay. I don't know why they didn't do that, but that's why they didn't do 0 to 2. This part, no sweat, but that part you couldn't have x equals 0, okay? Okay. Now, I wish they showed the picture. I don't want to draw it. If you look in your book, you'll see the graph of that. It is a smooth, continuous curve from 1/2 to 2, okay? X equal 1/2 to 2. All right, so it is smooth and continuous, the derivative everywhere defined, so all that kind of stuff. Now, I don't like that form either, okay? Maybe I'm just being picky about it, but it seems like it would make a lot more sense to have the least common denominator, which would be what? 6. 6x. You have to have the x in there too. So on this one, you go 6 into 6x will be x times x cubed would be x fourth plus 1, right? Oh wait, I'm sorry, no, 3. Is that what you said? I sort of got lost with what I was doing. Yeah, because 3 over 6x would be 1 over 2x, right? Are we in agreement there? Now that may not be any better. I just sort of like it better. Maybe I don't. Might be easier to do this, okay? Because you see, if you take this out, that gives you x fourth over 6x, which would be x cubed over 6. That's right. And take this out, and you get 3 over 6x, which is 1 over 2x. Now, I don't know. Maybe I don't like that one better, but it just seems like it looks better anyway. Okay. Now, what's the first thing you're going to do to it? Take a derivative. I'm beginning to second guess myself here. I'm going to write this in yet another way. 1/6 x cubed, that's the same as first, plus 1/2 x to the minus 1. I think I like that better than either of the other two. Because that's easier to take a derivative of, isn't it? So let's take the derivative of that. So first thing we do is take a derivative. Y prime is equal to what? 1/2 x squared minus 1/2 x to the negative 2. Perfect. I like that better. Okay. Now, what we're going to do next is square that, right? Because y prime squared. Remember our form. The arc length is going to be a to b of 1 plus y prime or f prime squared dx, right? Oh wait, to the 1/2, the square root of that. Okay, hit whichever way you want to do it. I like to the 1/2, but I'll do it like this because that's how the book did it. What's that? That's called the arc length formula. That's how you measure the arc length, how you integrate to get the arc length. So we've gotten our y prime. We need to square it now. Y prime squared would be what? Let me do one other thing. Let me go on and pull out the 1/2. And that gives me x squared minus x to the minus 2. Say again? Not yet. We haven't squared it yet. No, I wrote it down, but I didn't square it. So when you square 1/2, you get 1/4. Now square that thing. Anybody? X to the 4th. Good first step. No, it's a minus, isn't it? Okay. Yeah, hold on just a second. Okay. Wait. I can't get my pen back. There we go. All right. Yeah. Now, we pulled out the 1/2 squared in. That's X to the 4th. Now we do twice the product, right? So minus 2 times this and this, and that's 1, is what you're saying, right? So it's actually a minus 2, right? Yeah, because when you do a plus b squared, or a minus b squared, let me do that one since that's what we got here. Okay. That becomes a squared minus 2ab plus b squared, right? Twice the product of the two. If you don't believe me, FOIL it. A minus b times a minus b. A times a is a squared. Then you have minus ab minus ab. That's minus 2ab plus b squared, right? Okay. Well, the big question, is it right? Whether it looks right or not, you know.
So you tell me x squared times negative x to negative 2?
Negative 2. Yeah, because, okay. Let's FOIL it. Okay, wait. Yeah, you're squaring this. We squared this and we're squaring this. So this will be 1/4, that's that squared. This will be x squared minus x to the minus 2 times x squared minus x to the minus 2. Okay? That would be 1/4. That's on the outside. This will be your x to the... Yuck! I can't write. I get to going too fast and botch it up. Okay. That would be x to the 4th. And then you have a minus 1, which is what you're saying, right? And then you do that and you get another minus 1, don't you? Okay. Okay. Oh, I'm sorry. And then you do that one and you get a plus x to the minus 4. Right? Okay. So that's your minus 2 plus x to the minus 4. All right. Are we in agreement now? Or it still doesn't look like it? Okay. It's okay. All right. Now, I'm going to do a little bit of a weird thing here. I did all that of pulling it out. Now I'm going to put it back together. That's x to the 4th over 4 minus 1/2 plus x to the minus 4 over 4. I'm multiplying the 4 back in. 1/4 back in. Right? What's that? What? X? No, these are added. They're not multiplied. If they multiply, they cancel. Adding, they're not. Okay? This would be the same as plus 1 over x to the 4th. This is just x to the 4th over 4th. Yeah. Okay. Now, this is the thing we add 1 to. Right? But instead of adding 1, I'm going to add 2/2. Is that not the same as 1? Okay? So if you do that, then this becomes x to the 4th over 4. And when you add these two together, you get plus 1/2. Okay? Right? Because minus plus, okay. Plus x to the minus 4th over 4. Right? Okay. So that's adding 1 to it. But I don't like that too much. I want to make this 2/4. Is that all right? Okay. Now I'm going to pull the 1/4 back out. and I have x to the fourth plus 2 plus x to the minus fourth. Don't I? Now that's a perfect square. That is exactly a perfect square of 1/2 of x squared plus x to the minus 2. If you don't believe me, go back and do it. Okay? Because you see, the next thing we do after we add 1 to it is take the square root of it. Remember, square root of that thing. And the square root of 1/4 is 1/2. And the square root of this thing, this is exactly just like this one was with a minus 2 in here. You put a plus in there, and you get a plus 2. Okay? So you wind up with something you can take a square root of, and that becomes your integral. And it's just all over the board here. Sorry about this. Your integral now is from 1/2 to 2. I still don't know why they started with 1/2. Know why they didn't do 0, but why didn't they do 1? I mean, that would have made more sense. Okay? Now, this thing here that we've been calculating through, okay, is exactly what this is right here. We took the square root of it, and so let's pull the 1/2 on the outside. This is on the outside, and it's the integral from 1/2 to 2 of x squared plus x to the minus 2 dx, which will be 1/2. I think you can do the antiderivative of x squared, right? What's that? Third over 3 plus, and what's the antiderivative of x to the minus 1/2?
X to the minus x to the -3.
No?
X to the
-1 over -1, that's why I changed the sign. Okay? And we're evaluating this from 1/2 to 2. Now, I have so much mess on the board, I can't read anymore. So let me erase at least this start over here. This is where I had to prove that that worked. I think this will work better for me. Integrating this thing. And that's going to be, first thing I'm going to do is take this x, add 1 to this. That's what I did here, right?
I just didn't see it.
Huh?
I was lost.
Okay.
So too much up.
Second?
It was too many numbers.
Yeah, I know. That's why I erased that other stuff. But you got what I did now? Okay. Add 1 to that, make it a -1, and then divide by -1, that changes the plus to minus. Okay. Without anything in the denominator except 1. Okay. So this I'm evaluating from 2. So this is 1/2 times, when I plug a 2 in here, that would be 2 cubed is 8/3, okay, minus, and 1 over 2, okay, that'd be a -1/2. I'm sorry, it keeps blinking up. That's quite what I'm having to hold the board, and when I do that, I mean hold my screen. When I do that, it makes, I don't know, the connections go weird. Okay? Okay, that's the first part, when I plug the 2 in here. Okay? All right, now I'm going to plug the 1/2 in there, but I'm going to do the minus of that. And, sorry, it's doing it again. Okay. Come on back. Come on back. It's so picky. I don't know why, but it is. Okay. So now I'm going to put a 1/2 in there. And 1/2 cubed is 1/8. But you got a 3 there too, so this is going to be a minus 1/24. Weird but true. Okay? Minus a minus, because it's minus because we're using the lower limit, but then you had a minus sign, so that's going to be plus. And what's 1/2 to the minus 1? Okay. All right. Now I got the 1/2 out front. It's completely out front. I'm just plugging 2 in here. 2 cubed minus 3 minus 1/2. That's the first one, right? Then minus plugging in the 1/2 here. So 1/2 cubed, is 1/8, and 1/8 times 1/3 is 1/24. That's a minus because we did this, but then a minus, this minus, that makes it a plus, and 1/1/2 is, x is minus 1 is 1/x, and 1/1/2 is 2, plus 2. All right. All right. Now we got to add all those things together. So 1/2 times, least common denominator is 24. So that's going to be 9 times 8, I'm sorry, 8 times 8. 3 will go into 24, 8 times 8 is 64 24ths minus 12 24ths minus 1 24th plus 48 24ths, all over 24. Is that right? Okay. My numerator, 64 and 48 is 112, if I'm not mistaken. Minus 12 is 100. Minus 1 more is 99. So that's going to be 99 over 2 times 24 is 48.
You did 1/2 cubed, you got 1/8. What you did with that 3 for the 24? You multiplied that by 8.
Yeah, okay. Let's see if I can stand up. All right. It's 1/2 times this mess, right? Least common denominator is 24.
I was saying when you plug it in, like, how you get 1/24?
Okay, back here. Okay.
How you just get 1/24 when you plug 1/2 in? Like,
Yeah, plug in 1/2 in here.
yeah, that's 1/8.
That's 1/8 divided by 3 is 1/24.
What you did, you supposed to multiply by 7.
Say that again.
You supposed to multiply by 7.
You're not dividing. Okay. All right. Let me erase some more scratch here if I can, so I'll have room to write. Let me erase this. Oh, it didn't erase. Let me erase this scratch down here. I'll go on and get rid of this too. I hope I won't need it again. I sure hope I won't need it again. Okay. Now, what you're asking about is, here we plugged in a 1/2. Okay. Just doing the 1/2 here. So that's 1/2 cubed is 1/8 divided by 3. Yeah, that's the same as multiplying by 1/3. Or dividing by 3. Yeah, exactly. So, now, okay. So, I wound up with 99 48ths, but 3 will go into both of those. That would be 33 16ths, isn't it?
Or 2.0625.
Or is that right? I didn't check it.
Oh, yes.
Yeah, 33 16ths. Okay. Or, and you actually, yeah. All right. Whew. Okay. Like I said, it's hard to come up with functions that when you do all that to it, is still something you can integrate. This happened to be one of them that you could. But we started with such a weird function And this was a mistake here. Writing it like this was the better way to go. Okay? And then when you take the derivative of this, that gives you this. Factor out the 1/2, and then you have this. Square that, and the 1/2 squared becomes 1/4, and then that becomes that. This thing squared becomes that. And then add 1 to that, and that would be adding 2/2 of this. That makes it a plus 2 in there. And then you look at that and say, well, that's a perfect square. If this was a perfect square of this, then this is a perfect square of that, with just a plus sign there rather than a minus sign. Lo and behold, okay? So now that you've added 1, you squared it, added 1, then you had a perfect square, your square root goes away. And you're left with just this. 1/2 goes out front, square root of, because you already took the square root of 1/4 and got the 1/2. And the square root of this thing was exactly this. So that's all you're integrating. Thank goodness. Okay. That was nasty enough to integrate, especially between 1/2 and 2. Why did they do 1 to 2? It would have been so much easier. But I guess they wanted you to have the experience of doing that. So carry that on through. And the rest is the arithmetic, really, and that's almost harder than the calculus was. Setting up the point. All right, so that's your example 2. And guess what? They also leave out example 3. So can I erase this? Okay. So erase this and go to, okay, yeah. Okay. Just remind myself, we go to 11:40, right? Yeah. Okay. So we got about 20 minutes or so. Okay. So let's do example 3. Find the arc length of the graph of y minus 1 cubed is equal to x squared. Oh, what a delightful looking period. On the interval 0 to 8, and I assume, yeah, that's on the x-axis. These are the x values, 0 to 8. Okay. What an incredibly great looking function this is, because you have cubes and squares of different variables and stuff. And since we're doing an interval 0 to 8, let's just assume we're going to do dx's. The x is going from 0 to 8. So let's get y as a function of x. So what would be the first thing you would do? We're going to try to solve for y. Cube root, exactly. Y minus 1 is equal to the cube root of x squared. How would you express that? X to the 2 over 3. The denominator is the root and the exponent is the numerator. Okay, now only one thing left to do. Solving for y. Add 1 to both sides. Now, I don't care whether you write it in front or behind. They write it behind. Okay? That'll be fine. So, your y is equal to x to the 2/3 plus 1. All right? Now, what do we do with that y? Take a derivative. So y prime is equal to 2/3 x to the negative 1/3. The rest is a piece of cake. Then what do you do with that y prime? Square it. Okay, so y prime squared is, help me? which is 2 squared is 4, 3 squared is 9. 4/9 x to the negative 2/3. Perfect. Okay, now what do we do with that? Next cell. Add 1 to it. That wasn't hard. Okay, and then what we do is take a square root of that. So that's what we're trying to integrate. We're integrating. Second. What did I do with it, or how did I get it? Okay. Did you get the 1/3? Okay. How do you get it right up here? Is that correct? Okay. When I take the cube root of this, the cube root of that, basically what cube root is you put. Let's see. The cube root of a squared, okay, the a keeps its thing, exponent, and the root becomes the denominator of your exponent. Okay, so that's exactly what we did there. We had x squared, take the cube root of that, that moves the 3 into the denominator. I just prefer writing it in exponential form. I don't like the radicals. They're hard to deal with. Okay? But, yeah. Now that was the 2/3 you were talking about, or was it this 2/3? The one up there, or this one? Oh, this one. Oh. Okay. I'm sorry. Okay. First you took a derivative of this, and that gave you 2/3 x to the minus 1/3, right?
So you square negative 1/3, you're going to get negative 2/3.
Yeah. When you have y to the a and square it, that's y to the 2a. When you raise a power to a power, you multiply the exponents. 2 cubed squared. Okay. That would be 2 to the 6. Well, let's see if that's true. 2 cubed is 8, and 8 squared is 64. Well, 2 to the 6 is 2, times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64.
So the exponent was 2 to the 3/4.
What's that?
If it was 2 to the 3/4 squared.
2 to the 3/4 squared. Is that what you're saying?
So that'd be 2 to the 6/4.
Yeah, okay. I mean, 2 to the 3/4 squared. That would be 2 to the 3/2. Yeah. 6/4 is 3/2. Right? Yeah. Okay? All right. Good questions. Excellent questions. Okay. I'm going to get rid of that too. Okay, sorry about that. I was answering the wrong question. Okay. So, we're finding the arc length on that interval. The interval is going from 0 to 8, and that is your x values. Okay? And then you've got the square root of this thing here, which is 4/9 x to the minus 2/3 plus 1 dx. Oh, what a pain. Okay. Now, I should have rewritten this earlier, so let me do it now. Sorry about this. I'm going to write this as 4 over 9x to the 2/3. I just moved that downstairs, plus 1. Is that all right? I should have done that earlier. I just put everything in the denominator. So I'm going to rewrite that as 4 plus 9 to 9x to the 2/3 over 9x to the 2/3. Is that okay? I just rewrote. This is this thing plus 1. Okay. First move the x downstairs with the 9. Okay. The plus 1 is already there. Well, then this 1 I'm going to write is 9x to the 2/3 over 9x to the 2/3, right? 1. Okay. So that's it. So 4 plus 9x to the 2/3 over that. Okay. Now, that is what's under my radical there. So let me go back. Okay. And rewrite this with that up there. That would be 4 plus 9x to the 2/3 over 9x to the 2/3. And all this is to the 1/2 power. I just don't like the radicals. I'm going to write it to the 1/2. Okay? Now, is that okay? Okay. So this is the integral from 0 to 8 of 4 plus 9x to the 2/3 to the 1/2 power over, I'm going to take the square root of that denominator. That's going to be 3x to the 1/3.
Where does 1/2 come from?
That's the square root. Remember?
Oh, okay.
Yeah. The square root of this thing. Okay. That's where that came from. Okay. Now, I'm going to try me a substitution here and see if that works. If u is this thing here, du would then be 2/3 of 9, which would be 6, x to the minus 1/3. Here we have x to the minus 1/3. So I think we can do this by substitution. Okay. All right. So I'm going to rewrite it slightly here. 0 to 8. 4 plus 9x to the 2/3 to the 1/2 times, I'm going to pull the 3 on the 1/3 on the outside. Okay, that denominator goes outside. And this will be x to the minus 1/3 on the inside. I'll just move that upstairs again, dx. Okay. This is the reason this is no more well organized is I'm trying to do it as I see it, as we get to it. So hopefully you'll see. If I did it magically, and this just happens to be this, then I don't see that's learning anything. So here we have let u equal the innermost part, the most complicated looking part of this. Well, that's the radical, okay? So that's going to let u equal 4 plus 9x to the 2/3, okay? Then du is equal to what? Anybody? 6x to the negative 1/3. Right? because the derivative of 4 is 0, so that's out of there. And 2/3 of 9 is 6 times x to the minus 1/3 dx. Okay. Well, then I'm going to pull that 6 outside. No, I'm going to divide by 6. Okay. So that wipes out, and that gives me an x to 1/3. So the over 6. So this now becomes, yuck. What I'm going to do is erase this line up here and start writing up there. That denominator, that thing here is going to be 1/3 times the 1/6. So that's 1/18 times the integral. Say again? Yeah, okay. And what you have here is u to the 1/2, because this is our u to the 1/2 du, I believe. Okay. Now, one thing we haven't done is changed our limits. So let's go back to our definition here and do so. Okay. When x is 8 to the 2/3. Let's do it this way. The cube root of 8 squared. What's the cube root of 8? 2. Squared is 4 times 9 is 36 plus 4 is 40. So our upper limit there is going to be 40. When x is 8, u is 40. Yo. Okay. Now, let's do the lower one. When x is 0, that's of course 0. Times 9 is 0. Plus 4. So that starts off at 4. Hey. All right. So that's going to be 4. Oh, excellent. Okay, anything for that extra point, huh? Okay, good deal. Thank you. All right. And by the way, the reason for that, I happened to mention this morning in class. I said, by the way, if you want that 2 bonus points, for getting your paper in this month, this is the last day in October. Tomorrow it's going to be 1 bonus point, and that's why I got a paper suddenly. That was a short while ago. Okay. So now we've changed our limits. I think we can go to town, can't we? Okay. So it's going to be 1/18. And what is the antiderivative of u to the 1/2? Help me, somebody. U to the 3/2, and say again, over 3/2, which is times 2/3. Got it. And we're going to evaluate that from 4 to 40. Oh boy. Am I looking forward to that? No. Okay. Now what I think I'll do, because the 2/3 is in there just like the 1/18, let's go on and multiply those together. 2 will go into 18 9 times, so this will be 1/27th. Okay? And we'll just evaluate this one. Oh man. That will be 40 to the 3, okay. I'm going to do it this way. The square root of 40 cubed minus the square root of 4 cubed. Okay? I pulled out my constants. So all I'm doing is the square root of 40 cubed minus this. Unfortunately, that's not a perfect square. It could be written as the square root of 2 root 10, right? Cubed. Yeah, I'm really tempted to say yes, but we can simplify a little bit. So let me go up here and do it. 1/27 times, now, like I said, that's the 2 root 10 cubed minus, and square root of 4, we know what that is. 2 cubed is 8.
Where did the 127 come from?
It was a trick. Okay. All right. Up here it was 1/18 times the 2/3. Now 2/3 is going to be by everything, so I did that. So 2 will go in the 18 9 times. 9 times 3 is 27.
Okay.
It was magic. That's all. Okay. Now, what a pain in the neck this is. Okay.
Oh, that DX is not out there.
What's that? I'm sorry. What'd you say?
That 127 right there looks like it's DX 127. That's on the other.
Oh yeah, that's separate. Yeah.
I was like,
Yeah.
what are we doing?
Yeah. They just got all messed up. Okay, so this is 1/27 times 80 root 10 minus 8. Okay, I'll explain what I did there. Of course, 2 cubed is 8. The square root of 10 cubed is square root of 10 times square root of 10 times square root of 10. Well, square root of 10 times square root of 10 is 10 times square root of 10. So 8 times 10 is 80, and I can't think of any way to make that any better. The only thing I might think of doing is writing this as 8/27 times 10 root 10 minus 1. I don't know. Oh, look how they left it. Shame on them. They left it as 1/27 40 to the 3/2 power, which is exactly what we had, minus 4 to the 3/2 power, exactly what they had. And then they did an estimate. So you didn't have to go, well, I mean, you could have done anything you wanted to. All right. Whew. Like I said, finding functions that when you take a derivative of it, square it, add 1 to it, and then take a square root is something that's integrable. They're few and far between. So that's why they come up with such weird functions. What's that? Oh, why not? Yeah. I mean, no, I don't know. The next one actually has a log of a trig function. So yeah, I guess we will. But the trouble is, we don't have time for the next one. So we will begin next time with example 4, top of page 477. Let me see what kind of homework exercises I can come up with. Yes, what you say? You ready?
Yes, sir.
Good deal. Okay, homework exercises here would be number 5. It's at calcchat.com. Either 7 or 9, they're both at calcchat.com, and 7's at calcview. Then any of the odds 11 through 19, they're all at calcchat.com. And then try any of the odds 21 to 29. They're all at calcchat.com. And then they have an approximation one. Let's wait on that one until we do a little bit more. Okay? Good deal.
See you on Monday.
All right. Have a good weekend. And of course, doing calculus will make it a good weekend, right? Good deal. So let me end this. All right, you too. Thanks. Yeah.